In this video, I'm going to introduce vectors, and I'm going to explain the topics currently shown on screen. If you're looking for information about only one specific topic, please use the timestamps in the description below to skip ahead to that part of the video. I'll start by describing the difference between scalars and vectors. Volume and temperature are examples of scalar quantities. They can be described by a number with a unit. For example, a temperature of 2 degrees Celsius is described with the number 2 together with degrees Celsius for the unit. This number with a unit is referred to as the magnitude of the scalar quantity. Force, displacement, and velocity are examples of vector quantities. They have a magnitude and a direction. We represent vectors with arrows. The direction of the vector arrow gives the direction of the vector. The length of the vector arrow represents the magnitude of the vector. In the figure to the right, we're showing the displacement vector of a truck. In this figure, the displacement vector is the blue arrow. This vector shows how the truck is displaced from its start position. The vector's direction is northeast, and its magnitude is equal to 1 kilometer. This displacement vector tells us that the final position of the truck is 1 kilometer northeast from its start position. The figure to the right now shows the displacement vector for a truck 2 kilometers northeast from its start position. The vector arrow still points in the same direction, but its length is twice as long, indicating a displacement of 2 kilometers rather than 1. We can use vectors to analyze the motion of a body. We can use them to track the position of moving bodies. We can use them to analyze the direction and magnitude of their velocities and accelerations. We can also use them to analyze the effects of forces acting on a body. A vector in a two-dimensional plane or in a three-dimensional space is a directed line segment. The directed line segment AB, now shown to the right, has initial point A and terminal point B. The notation for a directed line segment from A to B consists of the letters AB with a small arrow above the letters. Vectors are often written in bold-faced letters. For example, the vector u is equal to AB. One notation for the length of AB is AB between two vertical lines. We can call these vertical lines vertical bars. We'll cover more notations for the length of a vector later in this video. Two vectors are equal, or the same, if they have the same length and direction. Shown to the right are two vectors. U is equal to AB, and V is equal to CD. These vectors have the same length and direction, making them equal vectors. Different directed line segments represent the same vector if they have the same length and direction. AB and CD have the same length and direction, so they both represent the same vector. We initially defined the vector V as being equal to the directed line segment CD. We can also use AB to represent the vector V. These directed line segments represent the same vector. We can use AB or CD to represent the vector V. The directed line segment CD has the origin 0, 0 as its initial point. This represents the vector V in standard position. We normally represent vectors in standard position. A vector V with initial point 0, 0 and terminal point V1, V2 has the component form of V is equal to left angle bracket V1, comma, V2, right angle bracket. The numbers V1 and V2 are the components of the vector V. The component form of the vector V equals CD, shown to the right, is V is equal to left angle bracket 4, comma, 3, right angle bracket. The components of this vector V shown to the right are 4 and 3. And to clarify, we can refer to these pointed brackets as angle brackets. For a vector V with initial point A, x1, y1, and terminal point B, x2, y2, we can find the component form of the vector V, which is equal to left angle bracket V1, V2, right angle bracket, in the following way. V1 is equal to x2 minus x1, and V2 is equal to y2 minus y1. So for a vector V with initial point A, 1, 2, and terminal point B, 5, 5, V1 is equal to 5 minus 1, which is equal to 4, and V2 is equal to 5 minus 2, which is equal to 3. So the component form of the vector V shown to the right is left angle bracket 4, 3, right angle bracket. We can represent this vector in standard position by setting the initial point to be 0, 0 and the terminal point to be 4, 3. The vector V equal to left angle bracket V1, V2, right angle bracket is the position vector of the points V1, V2. So the vector V equal to left angle bracket 4, 3, right angle bracket, currently shown to the right, is the position vector of the points 4, 3. The length or magnitude of a vector is the length of any of its equivalent directed line segments. The notation for the length of a vector V is V between a pair of vertical bars. We can also represent the length of a vector V as V between two pairs of vertical bars. In this video, I'll be using a single pair of vertical bars. Similarly, we can express the length of a vector V equals AB as AB between a pair of vertical bars. For the vector V equals AB shown to the right, we can calculate its length by using the formula for the distance between 2 points. The length of the vector V, which is equal to the length of AB, is equal to the square root of open bracket x2 minus x1 close bracket squared plus open bracket y2 minus y1 close bracket squared, where x1 is equal to 1, y1 is equal to 2, x2 is equal to 5, and y2 is equal to 5. So the length is equal to the square root of open bracket 5 minus 1 close bracket squared plus open bracket 5 minus 2 close bracket squared. 5 minus 1 is 4, and 5 minus 2 is 3. 4 squared is equal to 16, and 3 squared is equal to 9. 16 plus 9 is equal to 25, and the square root of 25 is equal to 5. So the length of the vector v shown to the right is equal to 5. For a vector in component form, v equals v1, v2, such as the vector v equals 4, 3 shown to the right, we can calculate its length by using the following formula. The length of the vector v is equal to the square root of v1 squared plus v2 squared. In this example, v1 is equal to 4 and v2 is equal to 3. So the length is equal to the square root of 4 squared plus 3 squared. 4 squared is equal to 16, and 3 squared is equal to 9. 16 plus 9 is equal to 25, and the square root of 25 is equal to 5. So we've calculated that the length of the vector v shown to the right is equal to 5. I'll now describe and explain vector addition. I'll first demonstrate this geometrically, and I'll then demonstrate vector addition using vector components. Shown to the right are two vectors, u and v. The component form of the vector u is 3, 1, and the component form of the vector v is 2, 4. We can add these vectors together by placing the initial point of one vector at the terminal point of the other. In this example, we can place the initial point of v at the terminal point of u. We can see this now shown to the right. This gives us the resultant vector u plus v, now shown to the right. In this graph, the resultant vector u plus v extends from the initial point of u to the terminal point of v. We can calculate the component form of u plus v from the components of the vector u and the components of the vector v. The vector u in component form is equal to u1, u2, which in this example is equal to 3, 1. The vector v in component form is equal to v1, v2, which in this example is equal to 2, 4. u1 is the horizontal component of the vector u, and u2 is the vertical component of the vector u. v1 is the horizontal component of the vector v, and v2 is the vertical component of the vector v. We can see to the right that if we add u1, the horizontal component of the vector u, to v1, the horizontal component of the vector v, that will give us the horizontal component of the resultant vector u plus v. And we can see to the right that if we add u2, the vertical component of the vector u, to v2, the vertical component of the vector v, that will give us the vertical component of the resultant vector u plus v. We add the vectors u and v by adding the components of the vector u to the components of the vector v. U plus v is equal to u1, u2 plus v1, v2, which is calculated as open angle bracket u1 plus v1, u2 plus v2 close angle bracket. u1 is equal to 3, and v1 is equal to 2. u2 is equal to 1, and v2 is equal to 4. 3 plus 2 is 5, and 1 plus 4 is 5. So we've calculated the component form of the resultant vector u plus v from the components of the vector u and the components of the vector v. In this example, we drew a diagram to help us to explain the process. It's good practice to use diagrams when trying to solve calculation problems. But if you wanted to, you could do this calculation without a diagram, provided that you know the component form of the vectors that you're adding. I'll now describe how to multiply a vector by a scalar. When we say scalar, we're referring to a real number, such as 3 or minus 4.2. For a vector v equals v1, v2, and a scalar k multiplied by v is equal to kv1, kv2. For a vector v equals 3, 4, which is currently shown to the right, and a scalar 2 multiplied by v is equal to 2 multiplied by 3, 2 multiplied by 4. 2 multiplied by 3 is 6, and 2 multiplied by 4 is 8. So in component form, the vector 2v is equal to 6, 8. The vector 2v is now shown to the right. So we have so far that for a vector v equals 3, 4, and a scalar 2, the vector 2v is equal to 6, 8. When we multiply a vector v by a scalar k, if the scalar k is greater than 0, then the vector kv has the same direction as the vector v. If the scalar k is less than 0, then the direction of kv is opposite to that of v. The vector minus 1 times v is another way of writing the vector minus v. The component form of this vector is equal to minus 1 times 3 minus 1 times 4. Minus 1 times 3 is equal to minus 3, and minus 1 times 4 is equal to minus 4. So we've calculated the component form of the vector minus v to be minus 3 minus 4. This vector minus v is now shown to the right. It points in the opposite direction to the vector v. The length of a vector kv is equal to the absolute value of the scalar k multiplied by the length of the vector v. In the equation below, the vector kv between a pair of vertical bars represents the length of kv. The scalar k between a pair of vertical bars represents the absolute value of the scalar k. And the vector v between a pair of vertical bars represents the length of the vector v. The absolute value of the scalar k is the non-negative value of that scalar. For example, the absolute value of the scalar minus 3 is 3, and the absolute value of the scalar 4 is 4. For a vector v equals 3, 4, which is currently shown to the right, the length of the vector v is equal to the square root of 3 squared plus 4 squared. This is equal to the square root of 16 plus 9, which is equal to the square root of 25, which is equal to 5. The length of the vector 2v is equal to the absolute value of the scalar 2 multiplied by the length of the vector v. This is equal to 2 multiplied by 5, which is equal to 10. The length of the vector minus v is another way of writing the length of the vector minus 1 times v. This is equal to the absolute value of the scalar minus 1 multiplied by the length of the vector v. This is equal to 1 multiplied by 5, which is equal to 5. The vector minus v has the same length as the vector v, but it points in the opposite direction to the vector v. I'll now describe standard unit vectors. Any vector with length equal to 1 is a unit vector. The vectors I equals 1, 0, and j equals 0, 1 are standard unit vectors in the xy plane. Any vector v equals ab in the xy plane can be written as a linear combination of these standard unit vectors I and j. I'll explain this further with an example. The vector v equals 3, 4 is now shown to the right. This vector is equal to 3 times I plus 4 times j. When we add 3i plus 4j, that's equal to the vector v equals 3, 4. We can write any vector of the form v equals ab in the xy plane as a linear combination of I and j. To demonstrate this further, the vector v equals ab is equal to the vector a0 plus the vector 0b. This is equal to the scalar a multiplied by the vector 1, 0 plus the scalar b multiplied by the vector 0, 1. The standard unit vector I is the vector 1, 0, and the standard unit vector j is the vector 0, 1. Substituting in I and j, we get ai plus bj. So for the vector v equals 3, 4, we can write this vector as 3i plus 4j. So we can write a vector v equals ab as being equal to ai plus bj. The scalar a is the horizontal or I component of the vector v, and the scalar b is the vertical or j component of the vector v. We can write the vector v equals 3, 4 as being equal to 3i plus 4j. For this vector v, the scalar 3 is the horizontal or I component of the vector v, and the scalar 4 is the vertical or j component of the vector v. The vector 0 equals 0, 0 is the 0 vector. It's represented by the number 0 in bold, and its components are equal to 0. The 0 vector is the only vector with length equal to 0. And the 0 vector is the only vector with no direction. For a vector v, v plus the 0 vector is equal to v. And for a vector v, minus v plus the vector v is equal to the 0 vector. And for a vector v, the scalar 0 multiplied by v is equal to the 0 vector. To summarize, in this video, we've learned about scalars and vectors. We've learned about the standard unit vectors I and j. We've described vectors in component form and as a linear combination of I and j. We've learned how to calculate the length or magnitude of a vector. And we've learned how to add vectors and how to multiply them by a scalar. We can use vectors to analyze the motion of a body. We can use them to determine the position of moving bodies, to analyze their velocity and acceleration, and we can use them to analyze the effects of forces acting on a body. If you found this content useful, please subscribe to the channel to receive more content. Thank you very much for watching this video. See you next video.